In core type of transformer, two side limbs are there. Here in shell type, along with two side limbs, central limb is also there. In core type, concentric cylindrical winding type of arrangement is used. And in shell type, both the windings are wound on central limb and sandwich type of wiring arrangements are used. Suppose these are the 10 turns of LV winding, then 20, then consider 20 turns of HV winding, then again 10 turns of LV winding, then again 20 turns of HV, then again LV, and near to core is always LV. So whatever the white you can consider white turns, these are the HV winding turns, okay, and this magenta, these are the LV winding turns, okay. So you can find HV turns are sandwiched between LV turns. So sandwich type of wiring arrangement that is used in shell type of transformers. So here more cooling is there in core type, less cooling.
हम अपने स्क्रीन शेयर किए क्या नोट्स की?
हाँ, नहीं दिख रहा है क्या?
यस मैम, वो नोट्स की स्क्रीन नहीं दिख रही है.
हाँ, 1 minute. अभी दिख रही है? हाँ.
यस मैम.
हाँ, okay. Core, in core type, two side limbs are there. In shell type, along with two side limbs, central limb is there. In core type, both the windings LV and HV are wound on two side limbs. Inner one is near to core, initially LV layers, then above it HV, then again above it LV, like this concentric cylindrical type of wiring arrangement. And in shell type of transformer, suppose these are 10 LV turns, then in between sandwich HV turns, then again LV turns, then again HV, then again LV, and so on. And near to core is always LV turns. Okay, in between LV, you assume white one, these are the HV turns. Okay, so like this sandwich type of wiring arrangement is used. So because concentric cylindrical type of wiring arrangement and sandwich type of wiring arrangement. Shell type is used for high voltage application. Core type is used for low voltage application. In core type, more natural cooling is there, and in shell type, less natural cooling is there. And whenever it's a repairing or maintenance, easy to repair or maintenance of core type, easy to remove the windings here in core type compared to shell type. Okay, so and one more thing is there, whatever the flux produced in shell type by primary winding, total flux is in central limb, and then once it reaches over here, suppose it is flowing in upward direction, this is the total flux in central limb, and once it reaches over here, as the core is symmetric about central limb, flux will equally divide. Suppose 6 milliweber in central limb, so 3 milliweber will flow through one side limb, and rest 3 milliweber will flow through another side limbs. Means here, whatever, suppose this one flux flowing through central limb is a addition of phi1 plus phi2. So you can see it's an example of parallel magnetic circuit. Whatever, suppose this one is phi1 and this one is phi2, so flux get equally divided, isn't it? And in central limb, it's a total flux, summation of phi1 and phi2. So shell type core is an example of parallel magnetic circuit, and a core type core is an example of series magnetic circuit. Okay, so this is the difference between the two, shell type and core type. Third one is also there. These two are used from generation up to distribution to step up or to step down the voltage. Core type is smaller one and shell type is larger one. And berry type is also there. Berry type is this one. Whatever right now you can see on the screen, it's a berry type transformer. You can see its core is like a wheel of a bicycle. This one circle, and whatever the this portion coming out like spoke of wheel of bicycle. This one is also a magnetic core. So, and whatever the circular lines you can see, these are the LV and HV winding. Near to core is always LV winding. Okay. and low voltage winding insulation thickness is less. High voltage winding insulation thickness compared to LV will be more. Thickness of insulation depends on voltage range. More the voltage range, more will be the thickness of insulation. So here distributed magnetic field is produced, means flux is flowing through this circular portion, magnetic core, and it is also flowing, it radiates out through these limbs, you can say, which are along with radius. Okay, so wherever distributed magnetic field application require very type of transformer is used, but in electrical engineering from generation up to distribution, either core type or shell type you will find. These two only used. So this is about the types of transformer. Then we'll go for the transfer of parameters. This one, see here, transformation ratio we have seen, K is equals to E2 by E1 is equals to N2 by N1. This one formula you can use for transformer which is under loaded condition also and which is on no load condition also, both the cases. But when the transformer is at no load condition, when the transformer is at no load condition, means no load is there across it, we have seen E2 is equal to V2 and E1 is equal to V1. And from KVA rating, we have seen V2 by V1 is equals to I1 by I2, because KVA rating into 10 to the power 3 is equals to V1 I1 is equal to V2 I2. As load on transformer go on changing, KVA rating changes. Whatever the KVA rating given in on nameplate, it's a full load KVA rating. Okay, so you can equate V2 by V1 is equals to I1 by I2. So whenever it's a no load condition, then you can say E2 is equal to V2 and E1 is equals to V1. Okay, so when the transformer it at no load condition, K is equal, you can use this formula. K is equals to E2 by E1 is equals to N2 by N1 is equal to V2 by V1 is equals to I1 by I2. But when load is there, we have seen the voltage equation on primary and secondary. On secondary side, E2 minus I2 R2 is equals to V2, and on primary, V1 is equals to E1 plus I1 R1. Okay, when under loaded condition. Then when transformer is under loaded condition, we can't say E2 is equals to V2 and E1 is equals to V1. It is the case only for no load condition. Okay. Now here you can see, suppose it's a step up transformer, then N2 will be more or N1 will be more, or V2 will be more or V1 will be more for step up transformer.
It will be more.
Huh? Which one more? Your voice not clear. Which one will be more? If it is a step up transformer, which one will be more? N2 will be more, correct. That is V2 will be more step up transformer. So K you will get greater than 1 or less than 1?
Greater than 1.
Greater than 1.
Very good. K you will get greater than 1. Okay. This is called as step up transformer. Reverse is the case for step down. If it is a step down transformer, then N1 and V1 are greater, isn't it? Step down. So that is N2 and V2 are less. So K you will get less than 1 step down transformer. Okay. And when both are equal, N1 and N2 are equal, V2, step up and step down transformer is used from generation up to distribution to step up the voltage or to step down the voltage. Where this 1-to-1 isolation transformer is used, where N2 is equals to N1, V2 is equals to V1. Sometimes in electronic circuit, there is a need to isolate the two circuits. Magnetically, they are coupled, but physically isolated, because in transformer, all of you know, primary and secondary winding both are not physically connected to each other, isn't it? Means electrical connection is not there, but magnetically they are coupled on common magnetic core. So whenever there is a need to electrically isolate the circuit, means current flowing through one circuit will not flow to adjacent like this, means not in series or not in parallel, but they are magnetically coupled. So third one is used, isolation transformer, one-to-one transformer. Okay, MCQ question. If K is greater than 1, K is less than 1, K is equals to 1, which one transformer? Whether it is a step up or step down or isolation. And based on this formula, numericals. We will see the numericals also on that topic. Before that, we'll cover first transfer of parameters. Okay. So, transfer of parameters, now we are going to learn. Before that, whatever the parameters on primary and on secondary we'll see. See, this is the primary winding, secondary winding. Primary winding copper resistance we denote by, yes, primary and secondary winding copper resistance we denote by
R1 and R2.
very good, R1 and R2, isn't it? So what is this X1 and X2 that we'll see? We have seen about the leakage flux. Okay, if you remember, we'll show you this one page is 12. Leakage flux will show you. See here, V1 you apply, I1 flows through primary winding, it produces flux. Whatever the total flux produced by primary winding, not 100% completes its path through core. Core made up of silicon steel, its relative permeability is very high, opposition to the flow of flux is very less. That's why 95 to 98% flux, maximum flux completes its path through core. It helps in producing the output. That's why it is called as useful flux. 2 to 5% flux can complete its path through air, and this flux don't help in producing the output. That's why it is called as leakage flux. This one flux, leakage flux, is completing its path through air. Consider here air is there around this transformer. Air relative permeability is less, but it is not 0, it is 1. That's why opposition offered by the air to the flow of flux, it will not be infinity. It will be very high. That's why, but it is not infinity. It will be very high, but it is not infinity. That's why flux can complete its path through air also. And which one we call it as a leakage flux. That's why we can say whatever the total flux produced by primary winding is leakage flux plus useful flux. Okay, leakage flux completes its path through air and useful flux completes its path through core. This one we have seen previously. Now see, this leakage flux is coming in contact with n1 number of turns. Okay, while analyzing the circuit, transformer circuit, or during designing, when calculations are done, so to consider the effect of leakage flux, what is done, this leakage flux is coming in contact with n1 number of turns. This leakage flux is alternating. So what will happen as per Faraday's law of electromagnetic induction? Because of this leakage flux, will any EMF get induced in this n1 number of turns?
Yes, ma'am.
Okay, so that one induced EMF, you consider it's a EL1. So to consider this effect of induced EMF, along with resistance of primary winding, one leakage reactance is also considered. So primary winding, its equivalent circuit will be some resistance R1, which is very less, copper winding resistance, and leakage reactance, that is also less. You can mark it as a X1 or XL1. L stands for leakage. Okay. So like this is the equivalent circuit of transformer on primary. So primary winding leakage flux comes in contact with the primary winding itself. As per Faraday's law of electromagnetic induction, then EMF will get induced because of leakage flux. Consider that is the EL1, small EL1. So to consider this voltage drop, this one EL1 is nothing but it is a voltage drop across this leakage reactance. So along with the resistance on primary, leakage reactance is also considered. how much leakage reactance, its value, so that voltage drop across it will be equal to this induced EMF due to leakage flux. Same is the case on secondary also. When you connect load across secondary winding, here it is. When you connect load across secondary winding, current starts to flow through it. So the moment I2 starts to flow, it will produce its own flux. Again, the same thing, maximum flux will complete its path through core, and very less percentage of flux completes its path through air, like this. Okay, so whatever this leakage flux on secondary side, that is also coming in contact with secondary winding turns. So as per Faraday's law of electromagnetic induction, EMF will get induced in secondary winding. So consider it is EL2. So to consider this EL2, what is done on secondary side also, along with the resistance 1, leakage reactance is considered, and whatever the volt XL2 and whatever is the voltage drop across this leakage reactance is equal to EL2. Okay, so XL1 and XL2 in some books you can find these are marked as X1 and X2. So any of its symbol you can use. You can use either X1 or X2 and XL1 or XL2. So in transformer equivalent circuit, you can see it's R1, X1 and R2, X2. So R1, R2 are the copper winding resistance, and X1, X2 are nothing but it is to consider the effect of leakage flux. Voltage drop across it will be equals to EL1 and EL2, which are the induced EMF in primary and secondary winding because of leakage flux. Okay, so R and L, it is nothing but R and L. So this one Z1, you can call it as a Z1, R1 plus J XL1, and Z2 will be R2 plus J XL2. Rather than XL1, XL2, you can use X1 and X2. So here I have written, see, leakage flux, it comes in contact with N1 number of turns, induced EMF. To consider the effect of this on primary winding, this leakage reactance is considered, and whatever is the voltage drop across leakage reactance is equal to this one. Same is the case on secondary side. Okay, voltage drop across X2 is equals to EL2, which is equals to, because of leakage flux, induced EMF in secondary winding. Okay, now equivalent circuit of transformer will show you first. This is about the leakage reactance. This one, see here, this one phasor diagram also